So in class we went over the linear form of sugars. However, it's actually very relevant to talk about the cyclic form of sugars because it's actually the cyclic form of sugar that's the predominant form. So in solution, 98% of glucose is in the cyclic form, whereas 2% is in the linear form. So clearly the cyclic form is the much more favored form of sugar. So first, let's talk about how aldoses, that is sugars that are aldehyde containing, form a cyclic structure. So when aldoses form a cyclic structure, they form what's called a hemiacetal. And just to review for you guys, a hemiacetal is made when we combine an aldehyde group with an alcohol. So this forms our hemiacetal group. So when an aldose forms a cyclic structure, it also forms an hemiacetal. And in fact, it forms what's called an internal hemiacetal. So here's D-glucose. So carbons 1, 2, 3, 4, 5, and 6. And here's our carbonyl carbon. So that's our aldehyde. That's going to participate in the reaction, as well as the hydroxyl group. So the hydroxyl group that's attached to the last chiral carbon, in this case it's carbon number 5 of D-glucose, that is going to participate in this reaction. To help you visualize what this is going to look like, let's imagine that we took D-glucose and we rotated it 90 degrees counterclockwise. So here's D-glucose again on its side. And here is carbon number 1, 2, 3, 4, 5, 6. And let's imagine that these carbons were able to bend such that this hydroxyl group is near the aldehyde group. So this is what it would look like if it did that bend. So here's carbon number 1, 2, 3, 4, 5, and 6. And at this point, this hydroxyl group is going to react with that aldehyde group to form our hemiacetal. This is facilitated by a base. So a base can deprotonate that hydrogen, which will then give the oxygen a negative charge, so it's such that it's a better nucleophile. So then it can attack that carbonyl carbon. And those electrons are then going to go into the oxygen of the carbonyl carbon. Now that's not a stable structure, and so this is where some acid can stabilize this reaction. And so it can donate a proton to that negatively charged oxygen to essentially form an alcohol. So we had our reaction followed by ring closure to now give our now cyclic form of D-glucose. And as you can see, we've generated a 6-membered ring. So let's renumber the carbons and see where everything's going. So here's carbon number 1, 2, 3, 4, 5, 6. In our 6-membered ring, we have carbon number 1, 2, 3, 4, 5, and then oxygen is now part of the ring. So we have 6 atoms in the ring, and that gives us our 6-membered ring. So because it's a 6-membered ring, we call this a pyranose. So this is a 6-membered cyclic sugar. So some important things about this cyclic sugar. First of all, the carbon that's outside of the ring, we call that an exocyclic carbon. And so in this case, this is carbon number 6. When we formed this ring structure, we actually created a new chirocarbon. And in this case, this is carbon number 1. This new chirocarbon that's been produced, this is what's called an anomeric carbon. By the way, I just want to reiterate that in the cyclization reaction, typically it's the hydroxyl group of the last chirocarbon that's going to be facilitating the attack. That's going to actually do the attacking of the carbonyl group, which in this case is an aldehyde. Okay, so back to our anomeric carbon. So the anomeric carbon was the carbonyl containing carbon before it became a cyclic structure, and now it is a chirocarbon. It has 4 different groups coming off of it. Depending on the orientation of the hydroxyl group that's attached to the anomeric carbon and that of the last exocyclic carbon, in this case it's carbon number 6, that's going to determine whether the sugar is an alpha sugar or a beta sugar. If the hydroxyl group of the anomeric carbon is on the opposite side of the exocyclic carbon, that is, it's trans in configuration, we call this an alpha sugar. So as you can see here, this hydroxyl group that's attached to the anomeric carbon, it is on the opposite side of the exocyclic carbon. So this is actually an alpha sugar. So it's alpha D-glucose. If, on the other hand, the hydroxyl group on the anomeric carbon is on the same side, that is cis in configuration of the last exocyclic carbon, then we call this a beta sugar. So you can see here, this is also D-glucose. However, the hydroxyl group that's attached to the anomeric carbon, it's actually cis in orientation to the exocyclic carbon on that glucose molecule. So that's actually distinct from this sugar. So that makes it a beta sugar. So it's beta D-glucose. So when a sugar is drawn in its cyclic form, it's called a Haworth projection. So these represent Haworth projections of glucose, alpha D-glucose and beta D-glucose. Okay, so let's look at what happens when ketoses, so those are going to be your sugars with the ketone groups, when those cyclizes. Okay, when that happens, we form what we call a hemiketal. And the reaction mechanism is actually really quite similar, except instead of an aldehyde for making an hemiacetal, instead we start with a ketone, react it with an alcohol to get our hemiketal group. So an example of a ketose that we're going to cyclize is D-fructose. The mechanism of the actual cyclization reaction is very similar. So we have the hydroxyl group on the last chiral carbon. In this case, it's carbon number 5. So it's carbon 1, 2, 3, 4, 5, and 6. That is going to actually attack the carbonyl group in D-fructose. In this case, it's carbon number 2, and that carbonyl group is a ketone. So again, let's just go ahead and go through the reaction, but you should realize that it's almost identical to the hemiacetal reaction. So D-fructose, let's put it on its side by twisting it 90 degrees counterclockwise. So here's carbon number 1, 2, 3, 4, 5, and 6. And let's imagine that this molecule is going to bend around so that way the hydroxyl group that's attached to the last chiral carbon is close in proximity to the ketone group. So it's going to look something like this. So here's carbon number 1, 2, 3, 4, 5, and 6. And that hydroxyl group is going to attack that carbonyl carbon. This is, of course, going to be assisted by some base that will abstract the proton on the alcohol group, which will make the oxygen a better nucleophile for attacking that carbonyl carbon. And go ahead and draw my acid. So that's going to push the electrons up into the oxygen, which is then going to be protonated by acid. And we'll finally have ring closure to give us our new cyclic structure. So, if you notice, we now actually have a 5-membered ring. So a 5-membered ring is called a furanose. Okay, so let's look at where each atom is in this 5-membered ring. So let's just start by looking at the carbons. We have carbon number 1, 2, 3, 4, 5, and 6. So you can see that carbons 2, 3, 4, and 5 are part of the rings, whereas carbon number 1 and carbon number 6, those are outside of the ring. So those are our exocyclic carbons. We can see that the ring itself contains carbons number 2, 3, 4, 5, and then the oxygen that was attached to carbon number 5. It used to be an alcohol, now it's in the ring, and that's what gives us our 5-membered ring. So this is still D-fructose, but now we have to designate whether it's an alpha or a beta. So this carbon here, that's our anomeric carbon. So remember, that was a carbon that used to have an oxygen double bonded to it. Now it no longer does. It's now a chiral carbon. This hydroxyl group attached to it, we have to look at its configuration is relative to the last exocyclic carbon. So there's actually two exocyclic carbons here. It's carbon number 1 and carbon number 6. Since carbon number 6 is our last exocyclic carbon, that's what we have to actually compare it to. So the hydroxyl group is actually on the opposite side of carbon number 6. That is, it's trans in configuration. So therefore, it's alpha D fructose. Okay, I'm going to go over a shortcut to figure out whether your hydroxyl groups are going to be up or down in your Haworth projections based on the Fisher projection. Sometimes this can help students and sometimes this can confuse students. So if it confuses you, you might just want to not use this information, but if it helps you, it can be very helpful. If in the Fisher projection, the hydroxyl group is on the right, then it's going to be down in the Haworth projection. If the hydroxyl group is on the left in the Fisher projection, then the hydroxyl group will be up. And the exceptions to this are going to be the hydroxyl groups that are attached to your exocyclic carbons, as well as those that are attached to the anomeric carbons. And the last chiral carbon. So let's check to see if that is the case for glucose. Okay, so we see for D-glucose, on carbons number 2, it's right, left, right. We don't count carbon number 5 because it's attached to the last chiral carbon. We don't count carbon number 6 because the hydroxyl group is actually not left or right because it's not a chiral carbon. And if we look at the glucose at carbons number 2, it's down, up, and down. So sugars can interconvert between their alpha and beta anomeric form. And this requires going back from their cyclic to their linear conformations back to their cyclic conformations again. This property is what's called meter rotation. And it's because of this property for it to meter rotate, that is, it can actually linearize. If the sugar is a reducing sugar, meaning that it has a free anomeric carbon, that is, its hydroxyl group is not bound to anything, it can meter rotate. And so it can meter rotate into its linear form and react with an oxidizing agent. If the sugar is a non-reducing sugar, which means the anomeric carbon is not free, it cannot meter rotate into its linear form and react with oxidizing agents, meaning it cannot be reduced. Tollens reagent is a test that can detect the presence of aldehydes and ketones in a sample. So if there's aldehydes and ketones there, it oxidizes them and produces an elemental silver product. If a sample has a reducing sugar in it, then it's going to test positive in a tolerance reagent test. And that's because that sugar can either rotate into the linear form, which is going to either have the aldehyde or the ketone group in it. So for example, here's D-glucose. It can react with tolerance reagent, where the tolerance reagent will oxidize the aldehyde group of D-glucose, the linear form of D-glucose, into a carboxylate functional group, and then also produces silver. So because this produces silver, we call it the silver mirror test. It's an alternative name for the tolerance reagent test because if there is a reducing sugar in it, it's going to leave a silvery mirror surface on the inside of the test tube. Another test that detects reducing sugars is Fehling's test. So this is a test that detects sugar in a urine sample, and that's especially important for detecting diabetes because individuals with diabetes will have a lot of sugar in their urine. Let's talk about modifications and derivatives of sugar. We'll see, particularly when we get into polysaccharides, is that modifications and derivatizations are going to really impact the chemical and structural properties of this sugar, which is ultimately going to affect its function in the cell. So a common modification we'll see is phosphorylation. And that's something we'll often see in metabolism. So this sugar is alpha D glucose 6-phosphate. It has a phosphoryl group connected to carbon number 6. And this sugar is produced in the first reaction of glycolysis. And the importance of phosphorylation is it actually keeps glucose in the cell. So it prevents glucose from leaking out of the cell by phosphorylating it. Another common modification you'll see is sulfonation. So here is glucose that's been sulfonated, and the importance of this is that it actually gives the sugar a negative charge. Carboxylation is also a modification that is going to give the sugar a negative charge. So you'll see this in some of the polysaccharides that we learn in the next video, and that is going to impact the gelatinous property of the polysaccharide. You can have amino sugars. So this is where an amino group is substituted. Here we have an amino group substituted at carbon number 2. This is beta D-glucosamine. You might have heard of beta D-glucosamine being involved in being used in joints and cartilage. And that amino group can be further modified, so it can be acetylated. So here's an acetyl group attached to it. This says N-acetyl beta D glucosamine. And the significance of the N-acetyl amino group as well as the amino group is that it adds more potential hydrogen bonding groups to it. So those hydrogen bonds, or the ability for it to create more hydrogen bonds, is going to impact its function, which we'll also see once we get into polysaccharides. Okay, so now we're going to move on to disaccharides. Disaccharides are formed by linking two sugars together. That is, two monosaccharides together. And when we link two monosaccharides together, we form what's called an acetyl functional group. So to form an acetyl, we react a hemiacetal with a hydroxyl group to give us our full acetal. So let's see what this looks like in an actual disaccharide. So here's two monosaccharides. This is beta D-glucose. This is alpha D-glucose. To form a disaccharide, the hydroxyl group of one sugar will react with the anomeric carbon of the other sugar. So that other sugar that contains the anomeric carbon, that's going to have the hemiacetal. And so in the process of connecting those two sugars together, water will be removed in the process through a condensation reaction to form our full acetal. I forgot to show water being removed up here. So let's see what that looks like. So here's our first sugar. It's got an acetal group here. And then our second sugar, here's our hydroxyl group. And we're going to simply remove a molecule of water in between those two sugars to form our bond. So they're going to be connected together by an oxygen atom. So the bond between the sugars is called an O-glycosidic bond. So this is where you have a bond connecting to a sugar at an oxygen atom. The end with the free anomeric carbon is commonly called the reducing end. And that's because normally the molecule can mutorotate at that sugar. So let's look up here at our disaccharide. So on this first sugar, here's our anomeric carbon. And then on the second sugar, here's our other anomeric carbon. So there's two anomeric carbons in this disaccharide, but only one of the carbons can be considered to be the reducing end. So this carbon, since it's bonded to the second sugar, this is not a reducing end. It cannot linearize or mutarotate. However, this sugar, since that hydroxyl group is free, so it's not bonded to anything, then that sugar can linearize, it can mutarotate. So therefore, this is the reducing end of this disaccharide. Not all disaccharides are going to have a reducing end. Okay, so if both anomeric carbons are bonded together, then there will be no reducing ends in that sugar, and therefore it cannot freely mutarotate. So one other thing is thinking about the configurations of the bonds in the disaccharide. Okay, which is that the configuration is going to be retained in the glycosidic bond as it was in the monosaccharide. So what do I mean by that? So let's look at these two monosaccharides and the configuration of the hydroxyl group that's going to be involved in the O-glycosidic bond. In beta-D-glucose, this hydroxyl group is beta. It's pointing up. And so in the bond, it's going to stay up once it's in the disaccharide. And we can see that is the case. Here, we see that in alpha-D-glucose, the hydroxyl group at carbon number 4, that is down. And so in the actual bond within the disaccharide, that bond is going to stay down. So all of your bonds are going to retain their configuration as they were in the monosaccharide once they are in the disaccharide. Now, there is actually a systematic way to name a disaccharide. However, it's somewhat complex, and also I don't really think it's that useful. A useful thing to learn. It's just more information that you have to retain without it serving a purpose. So what I really want you to be able to do is be able to identify the sugars in a disaccharide, being able to identify the bond. And I'd also like you to be able to draw a disaccharide if I tell you which sugars are in the disaccharide, as well as what type of bonds are connecting the two sugars. So that means you have to at least understand the nomenclature of the glycosidic bond in order to be able to do so. So, in the nomenclature, you need to indicate the orientation of the anomeric carbon in the bond, whether it's alpha or beta. So here's our disaccharide again. And here's our anomeric carbon. So since that bond is cis to the exocyclic carbon, it's a beta orientation. We also want to indicate the carbon number of the anomeric carbon in the bond. And this is going to be the first sugar that we're going to name. So here's our sugar. Here's carbon number 1, 2, 3, 4, 5, 6. So since that's carbon number 1, so I added a 1 here. And then we also want to indicate the carbon number of the second sugar in the bond. This may or may not be the anomeric carbon. So in this case, in our second sugar, this is carbon number 1. So 1, 2, 3, 4, 5, 6. So in this case, it's carbon number 4 that's in the bond, which is also not the anomeric carbon. So we're going to add 4. So it's a beta 1,4 O-glycosidic bond. You might also see it look something like this. Beta 1,4 glycosidic bond. So your job is going to be able to identify the bond, but as well as be able to draw a disaccharide if I gave you the monosaccharides that are going to be in it, as well as the type of bond that's linking the sugars together. This last page is a diagram of a number of sugars that exist, and you don't have to actually memorize these sugars or know how to draw them. It's just that this diagram is going to be important for helping you answer some of the questions on your problem set. So just make sure to have this this diagram handy when you're working on your problem set.